Hello everyone and welcome to the clustering section of the course. We've seen how to deal with labeled data, but what about unlabeled data? Often you'll find yourself trying to create groups from data, instead of trying to predict classes or continuous values. This sort of problem is known as clustering. You can think of it almost as an attempt to create labels. You input some unlabeled data, and the unsupervised learning algorithm returns back possible clusters of the data. This means you have data that only contains features, and you want to see if there are patterns in the data that would allow you to create groupings or clusters. This is a key distinction from our previous supervised learning tasks, where we had historical labeled data. Now what we're going to try to do is have unlabeled data and attempt to discover possible labels through clustering. By the nature of this very problem, it can be difficult to evaluate the groups or clusters for quote-unquote correctness. A large part of being able to interpret the clusters assigned comes down to domain knowledge. So for example, maybe you have some customer data and then you cluster them into distinct groups. It's going to be up to you and your domain knowledge to decide what those groups actually represent. Sometimes this is really easy, and other times it's really hard. For example, you could cluster tumors into two groups, hoping to separate between benign tumors and malignant tumors. But there's no guarantee that the clusters will fall along those lines. It will just be split into the two most separable groups. Also, depending on the clustering algorithm, it may be up to you to decide beforehand how many clusters you expect to create. A lot of clustering problems have no 100% correct approach or answer, and that's just the nature of unsupervised learning in general, since you never had those labels to check against. So let's continue on by discussing k-means clustering, a specific clustering algorithm which is unsupervised learning. So if you want more background on k-means clustering and the mathematics behind it, read Chapter 10 of An Introduction to Statistical Learning. K-means clustering is an unsupervised learning algorithm that will attempt to group similar clusters together in your data. So what do typical clustering problems actually look like? You can cluster similar documents, cluster customers based off their features, do market segmentation, identify similar physical groups, and much more. The overall goal is to divide data into distinct groups, such that observations within each group are similar. So we can see here on the left what an example of unlabeled data would look like if you plotted it on two features. One features on X, one features on Y. K-means clustering is going to attempt to cluster that data into distinct groups that we can see on the right. So you can see here it's almost discovering those labels, in this case represented by colors. So the k-means algorithm does the following steps. You, as the user, have to choose a number of clusters k. So you have to choose that before you actually initiate the model. That means you're going to have to use domain knowledge to choose a reasonable k value. Then it's going to randomly assign each point to a cluster. Until clusters stop changing, it's going to repeat the following. For each cluster, it's going to compute the cluster centroid by taking the mean vector of points in the cluster. Then, it will assign each data point to the cluster for which the centroid is the closest. So let's actually see this in action. On the very first panel, on the top left, we have our data. It's unlabeled, and it's totally ready to go for clustering. Then we have step 1. In this case, we've chosen k to be equal to 3. So we randomly assign each point to one of the groupings of k. Then we're going to do, on our first iteration, which we'll call step 2a, we randomly place the centroids on top of our data. Then, on iteration 1, step 2b, that's on that bottom row, we assign the individual data points to the actual grouping for the centroid they're closest to. Then, on iteration 2, step 2a, what we end up doing is moving those centroids to the average of all the vectors from connecting from that data point to the actual centroid. And then we keep repeating this result until the centroids stop moving. And then eventually you have your actual cluster groups. So again, choosing a k value. This is going to be a pretty difficult decision, or maybe a really easy decision. It really depends on the domain knowledge and what the data looks like. Depending on what k value you choose, you may get various groupings, and some of them may be obvious or intuitive choices, and other ones may be completely unclear. Here you can see some of that similar data with different k values chosen. Some of these look to be making sense, other ones don't look to make sense at all. It really depends on what your data looks like. So as I've mentioned before, kind of the shadow of unsupervised learning algorithms is that there aren't really easy answers. And in this particular case, there's no easy answer for choosing a best k value without specific domain knowledge. One mathematical method you could use is called the elbow method. So what you end up doing is you compute the sum of squared errors, otherwise known as SSE, for some values of k. For example, k equals 2, k equals 4, k equals 6, etc. The SSE, that sum of squared error, is defined as the sum of the squared distance between each member of the cluster to its actual centroid. Then what you end up doing is you plot k against SSE, and you will see that the error decreases as k gets larger. And this is because when the number of clusters increases, they should be smaller, so each distortion is going to be smaller as well. The idea of the elbow method is to choose the k at which the SSE decreases abruptly. So this produces what's known as an elbow effect in the graph. So you can see this in the following picture. So here we can see we have the number of clusters chosen and the within groups sum of squares. And you can see that around 5 or 6, you get this abrupt drop. So that's known as the elbow method because it kind of looks like the elbow of an arm. So that indicates that choosing around that point is a good k value. And hopefully you also have domain knowledge that helps drive that decision forward. So as far as plotting, PySpark by itself doesn't support a plotting mechanism, but you could always use collect to get back a Python object such as a list or an array, and then you can plot the results with matplotlib or other Python visualization libraries. Okay, so as far as the elbow method, don't take that as a strict rule when choosing a k value. As I keep mentioning, a lot of it depends more on the context of the exact situation, otherwise known as domain knowledge. So we'll try our best to get a feel for this with the examples in the consulting projects. Alright, let's get started by walking through the documentation example for k-means clustering. I'll see you at the next lecture.